Um, Hi, everyone. I'm very happy to introduce Korakit Seemakhupt. Korakit is a fourth-year student at the Department of Computer Science at the University of Virginia. His research interest focuses on computer network storage systems and the prototyping of systems using emerging technologies. So he has a very exciting talk to us about PMNet, and Korakit, I'm looking forward to your talk.
Thank you for the introduction. Good afternoon, everyone. I'm Korakit, and I'm going to talk about our work, PMNet, a system that accelerates update requests by persistently storing data in network. This work has been done in collaboration with Si-Hang Liu, Yasas Sivane, Mohammad Shabazz, and Samuel Khan. And this work was presented in ISCA last year. For the summary of this talk, I will start with an observation that data center applications usually store data in separate storage server and manage data through network. The latency of accessing remote data slow down the client, and in network compute, reduce the latency of stateless read requests, but not update requests. Our key insight is network device lacks persistent storage and cannot maintain data upon failure. Therefore, we propose PMNet that enhance P4 switch with persistent memory and locks requests in persistent memory in network to move server latency of update request critical path and use locked requests in order to recover from failure. We also integrate PMNet with replication and read caching. For evaluation, we program PMNet packet processing pipeline in P4 and implement the design on FPGA and evaluate whole system. The results show that PMNet significantly improved update request throughput and tail latency over client server baseline. Let's get started. I will start with the motivation of PMNet. For the motivation of this work, common application in data centers store data in separate storage server. For example, the front end of social networking and online transaction processing, such access storage backend, such as Memcached and Redis. The latency of accessing data in storage server is critical to performance of these applications. In case of Redis, our breakdown showed that 70% of the latency is from the server side. Next, we want to see where the latency comes from. When the client sends a request to access data in the server, the request is forwarded through the network stack of the client through the network and entering the network stack of the server. The request is then processed by the server, and the server sends the response to the client, during which the client stops waiting. To mitigate server-side latency, in network compute adds application logic in network device to reduce the latency of computing tasks. Another approach is by passing volatile cache in network to serve read requests. In network cache moves server latency of some read request critical path, but can we apply the same idea for update requests? For update requests, because failure can happen while the request is being delivered to the server and causes data loss. The client needs to wait until it receives response from the server because it needs to ensure that the result of an update is persistently stored on the server. Thus, caching data in network without persistent storage can cause data loss upon failure. Next, I will talk about the key idea of PMNet, which is in-network data persistence. To reduce the blocking time of update requests, PMNet adds persistent memory to network device. Persistent memory allows network device to persistently lock update requests. Here's how PMNet persistent locking works. Upon receiving an update request from client, PMNet locks the request in the persistent memory, and after the request persists, PMNet sends the ACK to immediately unblock the client, and at the same time, forward the update request to the server. The server then processes the request of the critical path. Therefore, PMNet unblocks the client before the server responds and enables sub-RTG data persistence in network. However, there is a challenge for persistent locking. That is how to recover lost requests while failure happens before the server processes request. For example, after the client sends an update request, PMNet device locks the update request and sends the ACK to the client. Then failure happens before request arrives at the server. Since the client is unblocked and has proceeded to the next operation, it cannot resend the request. In order to recover from missing requests, first, server detects failure using timeout or heartbeat signal. Then the server sends the transmit request to PMNet device. PMNet device read locked update request in the persistent memory and resend it to the server. The server then processes requests normally. Therefore, PMNet recover lost requests from persistent locks in PMNet network devices. Next, I will talk about PMNet design. That is how PMNet enables in-network persistent locking. For the design, I will talk about two parts. First, PMNet hardware pipeline, and second, PMNet protocols. I will talk about the hardware first. For the hardware, traditional programmable switch or NIC packets are forwarded to the destination according to a rule programmed in the match action table, which we call MAT here. On the other hand, PMNet NIC and switch adds lock queue that buffer requests from MAT pipeline, and the persistent memory that store locked requests. Thus, in addition to forwarding incoming packets, PMNet MAT pipeline control the access to the persistent memory. PMNet MAT pipeline is implemented in P4 and is compatible to most P4 support network devices. On the other hand, locked queue and memory controller are implemented in native hardware description language because P4 does not directly have support for persistent storage. Next, I will talk about the protocol. For PMNet protocol, PMNet is built on top of UDP protocol by reserving specific UDP ports. PMNet header consists of 4 fields: type that determine different PMNet packet types, session ID that use different PMNet session, sequence number that used for request ordering, and hash value that used to index the request in the persistent memory. The header is defined in P4 here. A PMNet device performs different operations based on type field that define packet type. We will see how PMNet handle each type of packet. For non-PMNet packet, the packet is forwarded directly to the destination. For the update request, PMNet first lock update request in the persistent memory. And after the request persists, PMNet sends the ACK to unblock the client by manipulating original requests from the client. And at the same time, PMNet forwards requests to the server. Therefore, PMNet locks and forward update requests and send the ACK to unblock the client once the request persists in the persistent memory. For the ACK packet, which indicate that the server has processed requests, PMNet remove associated lock entry in the persistent memory and also forward the ACK to the client. For retransmit requests that server sent when the server is recovering from missing packet, PMNet looks up in the locked request in the persistent memory, read the locked request, and resend it to the server. The retransmit request is generated by combining original locked requests from persistent memory with new incoming retransmit request, and also forward request to the client. For bypass requests, which the application sent when it wants to update the server directly, such as synchronization primitives, PMNet forwards requests directly to the server. Next, I will talk about PMNet integration of read caching and replication. Apart from locking update requests to move server off the critical path, there are additional applications of PMNet. Those are accelerating replication and serving read requests with caching. First, I will talk about replication. For replicated server without PMNet, when the primary server receives an update request from the client, it replicates the request across all replica. Only after all replica finish processing the request, the primarily sent response to the client. We can see that the replication increased latency of an update request. In order to accelerate replication, PMNet locks update request input in multiple devices to protect against hardware failure. For example, in this example, two-way replication, there is two-way replication on the server. And the update requests are also locked into PMNet devices. When the request sends an update request, the request is locked in PMNet devices. The client waits for 2 ACK, each sent by different PMNet device. This ensures that the request persists in both PMNet devices. Then the request is forwarded to the replicated server of the critical path. We can see that PMNet exploits persistent locking to provide data redundancy and move replication latency on the server of the critical path with small overhead. Therefore, PMNet exploits persistent locking to persistently replicate data in network. Next, I will talk about caching. For the integration of read cache, first, PMNet locks incoming update request and forward it to the server. Upon receiving read requests, PMNet exploits recovery mechanism to look up the request in the persistent memory. And if a lookup is a hit, PMNet uses locked update request to respond read request. Otherwise, PMNet forward the read request to the server. Thus, PMNet exploits locked update request and recovery mechanism to accelerate read requests. Next, I will talk about the evaluation. For the evaluation, we implement PMNet on Xilinx Autoscale Plus evaluation platform. We program the MAT pipeline in P4 and implement the pipeline on the FPGA using Xilinx P4 SDNet toolchain. We use DRAM to emulate persistent memory and use QFSP port as network interface. Note that our server is equipped with persistent memory to optimize storage performance. For the design comparison, we implement PMNet both as a bump in the Y in server's NIC and as a bump in the Y in serverless Tor switch, and compare them against the client server baseline, which only store data in the server. For the workloads, we use micro benchmark to test raw performance of our evaluation hardware and use persistent memory optimized data store workload to evaluate application performance. For the first experiment, we want to see the performance of PMNet device. We use an ideal handler on the server that immediately responds to the client. The figure here shows the latency bandwidth of different setups. Y-axis shows the latency and X-axis shows the bandwidth. Red line here shows the latency bandwidth of client server setup. We can see that the client server baseline achieves maximum of bandwidth of around 10 gigabit per second, which is a line rate. While the blue line here shows latency bandwidth of PMNet in switch setup. We can see that the maximum bandwidth is similar to baseline, but with considerably lower latency because server network stack processing is now out of the critical path. While the dashed line here shows PMNet in NIC configuration, which have similar performance to PMNet in switch. Therefore, by removing server out of the critical path, both PMNet in switch and PMNet in NIC offer the same benefits of lower latency and same bandwidth as client server baseline. We refer to PMNet in switch only as PMNet for radar results. Next, we evaluate application performance. The figure here shows average update latency for key value store type workloads. The X-axis indicates the workload and Y-axis shows average latency of update request. We can see that PMNet effectively reduced update request latency by moving both server network stack processing and application processing out of update request critical path, especially on read optimized workloads such as skip list, which has long latency for update operations. Next, we evaluate update request tail latency of key value store application. Figure here shows the latency distribution of update requests in Redis. X-axis shows the latency of the request and Y-axis shows the CDF of the request. Red line here shows the latency of baseline client server setup, and the blue line shows the latency of PMNet setup. We show Redis workload as example. Other workloads follow similar trend. We can see that for Redis workload, PMNet decreased tail latency of update requests by 4.5x. Therefore, because PMNet persists update requests in hardware with predictable latency, PMNet significantly improved tail latency of update requests. Similarly, we evaluate performance of mixed read and update requests in 50-50% ratio. We can see that while half of requests which are update requests are accelerated by PMNet, read request performance remain the same. Thus, PMNet without read caching only improve update performance. On the other hand, with caching shown in yellow line, PMNet exploits recovery mechanism to respond read requests and improve latency of read requests. For replication, we compare the performance of baseline client server with and without replication on the server, with against PMNet, both without any replication and with replication in both PMNet device and on the server. The graph here shows the latency of update requests on y-axis. The results show that PMNet with replication reduced update latency by 5.9x over client server with replication. And the performance penalty of PMNet replication over PMNet without any replication is minor. Therefore, PMNet moves replication latency of the critical path while maintaining protection against hardware failure. For more details, you can see full results in the paper. For the conclusion, PMNet introduced new use case for in-network computing. That is, provide data persistent to network to accelerate update requests by enhancing existing P4 programmable switch with persistent memory. PMNet also accelerate replication and read requests. We also make the implementation of PMNet, including P4 source code, publicly available in the link here. Thank you. I'm ready to take questions.
Thank you for the interesting talk. I have a whole bunch of questions about how the system PMNet works. I am confused. It sounds to me like the main idea is that you're using persistent memory on a switch to act as a type of write-ahead log for some storage server. But I didn't understand. I saw you talk through a little bit of what happens if a message is dropped, but I didn't understand what happens if the switch fails. How do you recover from that event?
I see. So in case the switch hardware can fail, then we need redundant hardware, right? So that when the failover happens, it can switch to another hardware. But there are two main problems with that. First, if the switch fails, it means that the network path from the client to the server also failed, right? Then, well,
I suppose, I mean, one path at least, right?
Yes. So in order to continue the operation, that needs to be a path from the client to the server, right? And so one of our proposal to prevent this is to basically implement the PMNet as the top of the rack switch on the server side. And in order to prevent, to provide redundancy for the TOR switch, there are proposals that use multiple redundant TOR switch on the server side, on the TOR switch, yes. And yeah, and
so you would have redundant switches.
Yes.
But then the client, do they need to, I mean, how do you make sure that the redundant switches stay consistent with each other?
Right. So when in normal operation, so we may route the packet through only one switch, right? But in this way, we need to route the traffic to both switches. And when a failure happens, basically one of the switch is taken out and we can switch to other switch that's still available.
I see. I had another question is, you talked about a packet loss from the switch to the server, but it seemed like packets could be lost at multiple places, say from the client to the switch to the server, or from, on the response back.
I see.
And it wasn't clear to me how you know where the packet was lost. I guess what I'm worried about is it possible that you could get multiple updates at the same time and not know it? How do you guard against that?
So your question is, provided that failure can happen at many places, there is a chance that, let's say, the client know that, okay, the client think that maybe sometime some kind of timeout mechanism, think that the request is lost and retransmit the request, right?
Yeah.
Right. In that case, when the client sends the request, it kind of it has a sequence number within the request is sent. So on the server side, it checks the sequence number. If it's the same, it's reject the new incoming request.
I see. And then I guess what I was wondering about was how this design impacts the network topology. I guess you know, if an update goes to a PMNet switch, is it possible for a different client to send a request that wouldn't travel over that switch but still hit the server, so they might get like a stale read?
For the read, in case we implement the read caching, right? We need to make sure that all client that is going to that server all requests need to go to the switch.
I see.
Because in that way, that's why we propose using a cache on the Tor switch of the server, because all requests need to go to that switch. So in that way, you do not need to kind of have the coherency between different switches.
Okay. This is really interesting and exciting work. I think the performance results look very promising. So I look forward to hearing more about this. Thank you for the talk.
Thank you.